right, chemistry students, we are going to start on Chapter 8. Chapter 8 is zooming in and looking in more detail at solids, liquids, and gases. So we're going to have most likely 3 videos. The first one is going to look at the states of matter in more detail, the solid, liquid, and gases, as well as changing states, for example, from solid to liquid and then liquid to gas. And then because gases are so unique, the second video will probably be all about gases and the gas laws, and the last video will be short and it'll just give some properties of solids and liquids separately. Okay, so these are the objectives. Like I said, this video we're going to start by just looking at the states, the 3 different phases and change of state, and then we're going to look at this new concept called intermolecular forces. Okay, so these are the sections, and I'm looking at the change of state, which is not really looked at until the later sections in Chapter 8, but I wanted to go over the different states and then just go straight into the change of state while they were all 3 fresh on your mind. Okay, so these 3 images you should already recognize and understand. On the far right we have the solid, closely compacted, definitive volume, definitive shape, and these molecules are vibrating, so sometimes you see like little vibration movements in the images, whereas the liquid, they're more spaced out, they are moving relative to each other and take the volume of their container, but they don't, and the shape of their container. Okay, whereas gases, these sort of tails on the spheres, gases, you're thinking a lot more space between them, moving a lot further apart, separated. Okay, so that shouldn't be new, that should be review. But we're going to look at changes between these because they involve some kind of a energy change, as we had already talked about in an earlier chapter, that you can actually apply it to delta H and delta S. You can look at the fact that gases have higher entropy, this S. So we're going to see some diagrams that have enthalpy in them as well, but you can actually apply it to delta G, the overall Gibbs free energy for each of these. Okay, so your book has an image, and we're going to come back to this image in a little bit, but this image starts with solid at the bottom, and then it shows the transition from solid to liquid and then liquid up to gas, as well as going back down in the other direction, stepwise or direct solid to gas and gas back to solid. If you notice, they've got color coordinated. If heat is released, it's in red. If heat is absorbed, it's in blue. So that's the image from your book, but I'm going to actually break it down because it even has on the far left delta H and delta S, and on the far right the same deal with the values that differ there. So I'm gonna break it down into just some individual steps, and then we'll come back to this. Okay, so hopefully everybody's familiar with, if you go from a solid to a liquid, that is melting. Now in this image, if we're adding heat, in this image they are using a red color. Okay, and if we're going the other direction, we are removing heat. Now, a lot of people don't think of freezing as removing heat, because usually if it's like, if you say, oh, it's freezing outside, you're thinking no heat. But you have to remove heat out of this liquid in order for the substance to have the property that it'll have when it returns back to a solid. Heat is getting removed out of the liquid. Where's it going? It's just releasing out into the atmosphere, into the surrounding air. Okay, so this is just solid and liquid. Okay, let's look at liquid to gas. So you have to add heat to go from liquid to gas, and we call that vaporization. And then gas back to liquid, we call that condensation. This is what is going on like on a hot summer day. If you have a, your water bottle outside, and so cold water is in here, and you're outside, it's maybe 95 degrees Fahrenheit, and you start to get little droplets outside, and people say, oh, your water bottle is sweating. Okay, what that actually is the water vapor in the high humidity atmosphere is condensing back into a liquid because there's kind of a cold bottle, cold temperature surrounding the outer plastic of your plastic water bottle. Okay, You can't call it sweating in chemistry class. We call it condensation, okay? And you need to know we are removing heat from the gas in that direction, okay? So hopefully you can recognize from this both of these processes, as well as the solid to gas and gas back to solid process, they are all reversible, okay? So you can go either direction, kind of like an equilibrium process. And I just want to add two vocab words that are not, they're on the next slide, but while we're on this slide, if you're going directly from solid to gas, that would be something like dry ice does that directly, dry ice. That is sublimation, and a lot of students struggle with that word, okay? And a gas back to a solid, that is deposition, okay? So those words are a little bit harder. Excuse me, those words are a little bit harder, okay? So these are individual images. Here is a diagram that did not come from your book, but it actually shows, so it's a triangle, so solid, gas, and liquid, and you can think of it like equilibrium among all three states, the solid, the liquid, and the gas. And if you see, this diagram shows in red heat absorbed, and in blue the arrows heat released, and it shows there's the sublimation and the deposition that I wrote on the previous slide. And then here's, for example, the liquid to gas vaporization direction. So you should recognize, you should be familiar with, here's the solid vibrating, be familiar with if we're going in this direction, are we adding heat? Yes. Whereas freezing, we're taking away heat from the substance. Okay. So you need to be familiar with all of that, whether heat's getting added or removed, okay? Whether heat's getting, whether the substance is a solid, liquid, or a gas, what phase we're in, that kind of thing, okay? So let me give some actual numbers to this instead of just saying heat, all right? We've already gone over enthalpy and entropy. Here's the melting, and we can just stick with water. We can just say here, so this is like ice water, and then this is liquid water, okay? Liquid H2O, okay? You have a value, an enthalpy value here, that is the heat that is released, if that is going from it's released here, down if you're going from a liquid back to a solid, or the heat that is absorbed by the system if we're going from solid to liquid, the melting phrase, or melting component. Okay, so by the way, that may sometimes be called heat of fusion, okay? Heat of fusion. Fusion is just another fancy term for this enthalpy value, this positive 6.02. If you had it in a table in your book, it would be labeled heat of fusion, and then it would just give it as 6.02 kilojoules per mole. And you would need to know if we were going from solid to liquid, that it's a positive value. And if we're going from liquid back to solid, it's a negative number, okay? Like, because going from liquid to solid, this negative is exothermic, and the positive we already know, positive enthalpy is endothermic, okay? You can do the same thing with entropy, okay? With the entropy value, same melting, freezing, and you have an appropriate joule per mole Kelvin, joule per mole Kelvin. Hopefully it makes sense that if we are going from a solid to a liquid, we have solid is kind of all of the close spheres, and liquid were more disorder, so we have a positive entropy value because there's more disorder in a liquid. Whereas if we're going from liquid back to solid, we have a negative entropy value because we're decreasing the disorder of the system, or the freedom of the water molecules is another word. This freedom is another term that's sometimes used. Okay, so now that you've seen that with just solid and liquid, go back and you should be able to understand what this diagram from your book is trying to show. I'm going back here. When it says, all right, if we're going in this direction, delta H and delta S are greater than 0. Whereas if we're going, for example, from gas to solid, delta H and delta S are less than 0, okay? So you can look at this diagram and you can assess it based on everything we saw on these slides, okay? So let's actually graph this change of phases or change of state process in a curve that we're going to call a heating curve, okay? So you really need to recognize this. Now, whenever you see a curve or a graph in a science class, the first thing you need to do is pay attention to what the axes are, what the x-axis and the y-axis are. So X is, in this case, just heat added, whether you have that in units of kcal per mole or kilojoule per mole. And then the y-axis here is temperature, okay? Sometimes I have actually seen the x-axis on a heating curve just be like progress of heat added or something like that, but you can just leave it as heat added. All right, so we have all three phases on here, but we have some extra terms, and there's your solid, image of your solid, liquid, and then the image of the gas. But you see there's the delta H, the heat of fusion, and then there's the delta H, heat of vaporization. That would be like the value in a table in a textbook, okay? But you're going to start at the very bottom, start at the bottom here where I'm putting the red dot, okay? And we have a substance. As heat is added, the temperature of that substance is rising. It is still a solid, but this pale blue line here, this beginning line that I'm not trying to draw over the line, I'm just drawing next to it, that entire process, your solid is just warming in temperature. So we're just warming the solid. But at this point here that I'm putting the red dot on, I'm going to make a note over here to the side. Solid starts melting. That would be the melting temperature of this substance, okay? Melting point. Here is still the melting point. See, it's labeled melting point. But at this point, if you notice, the temperature doesn't change between big dot on the left, and I'll make this like a square, and the square on the right. The temperature remains constant there. And what is happening in that flat line? What is happening? Well, let me say actually at the square. So at the square, all solid melted. Okay? So we are all liquid. You're all liquid. All the particles are in the liquid phase, okay? But the whole line, all we're doing is just the process of melting. So if you had 10 molecules, maybe at the circle dot, the first one starts melting, and by the square, all 10 have melted. From there, the green line, all we're doing is the same process, warming the liquid. Warming the liquid. Same process as the pale blue line where I wrote warming down here. We're just warming the liquid at the green line until we get to, hey, guess what? It's labeled boiling point. Okay, so that is where liquid, that says liquid, liquid starts forming the gas or the vapor. And I'm going to say vapor because it's delta H of vaporization. Okay, and that is going this horizontal black line here. The entire substance is changing into a gas throughout that process. So it's not warming. It's not going to warm anymore. The temperature remains constant until every single molecule is converted into a gas, okay? So the farther you get to the right, you have more gas than solid, or excuse me, than liquid, but the temperature isn't increasing. And then this far right spot that I'm circling here, at that point, all the liquid is now a gas, all in the vapor phase. And the red vertical or very, very steep line here, that's where the vapor is starting to warm, okay? So that is a heating curve for solids, liquids, gases, okay? You definitely need to know that, recognize that, and know when temperature is changing or not changing, when the phases are actually changing, being able to maybe label the melting point and boiling point. That's all important, okay? If you were doing a calculation with these, which we're not going to do, but I want to be clear, if you're doing a calculation with these, you would have to be given the mass of the substance and find in a table in the book, or as I'll show you on the next slide, or be given the heat of fusion or the heat of vaporization, and you could calculate the amount of heat for the phase change given, if you were given, say, 100 grams of water or 300 grams of water, what would be the amount of heat that would cause it to melt. That's kind of what you're thinking of, or boil if you're dealing with heat of vaporization. Okay, so your book has a table that actually shows a bunch of common substances, and I'm going to actually look at so water, since that's a familiar substance. Melting point is 0. Boiling point is 100 degrees Celsius. Okay, so that's nice, simple, easy numbers. All right, if you see here, we have the heat of fusion and the heat of vaporization. Okay, so that's what those two columns are that are representing the phase change from the appropriate phases. Okay, solid to liquid or liquid to gas. This isopropyl alcohol, that's like rubbing alcohol. That's a common substance used. Another substance, ethyl alcohol, also called ethanol. That's like the main substance in alcoholic beverages, but it's also used to sterilize equipment in like a hospital. Okay, and then common cleaning substance, ammonia. That's NH3, common cleaning substance. So if you look, it boils actually in the negative Celsius temperature. Okay. So what actually affects these melting points and boiling points and the appropriate heat of fusion, heat of vaporization? Why doesn't everything just boil at the same temperature or melt at the same temperature? Well, we have a process that's kind of a microscopic within the beaker. What's going on? We have a process that are intermolecular forces. Okay? I'm going to go through all of the intermolecular forces and describe them. This is section 8.2 in the book. But ultimately, while this change of state is fresh on your mind, what you need to know is that intermolecular forces are what cause higher or lower melting points, boiling points, that kind of thing. So if we have a lot of heat that must be added to a substance in order to change the state from solid to liquid or from liquid to gas, that means you have a lot of intermolecular forces present in that substance. If there's only weak intermolecular forces, then that substance will have a low boiling point. Okay? So what are these intermolecular forces? We've been looking at covalent bonds, ionic bonds. That would be, a carbon-to-carbon covalent bond. Okay, and then maybe you've got like hydrogens to satisfy the octet. Okay, so that's not intermolecular forces. Or maybe a sodium chloride with an ionic bond. That's not intermolecular forces. What we're looking at is if I had an entire beaker full of this substance here, okay, and let's just draw it as a big sphere. If I had a beaker full of them, let's just say I've got 6, there are attractive forces. I'm going to draw sort of dotted lines between the molecules, okay? And those are the intermolecular forces, okay? The covalent bonds and the ionic bonds, like in sodium chloride, those are within a molecule or a compound. So within a compound, you say compound if it's ionic, or molecule if it's covalent, okay? So just to be clear, within a molecule, the covalent and ionic, the intramolecular forces, those are the covalent and ionic interactions. Intermolecular forces that we're going to look at, there's 3 of them we're going to look at, are between molecules, okay? So this is a water on the left and a water on the right, and we have some kind of attractive force that's represented by this red dotted line. Here's a beaker full of some substance. They listed here as C5H12. And they kind of all look like this shape, but they've got a bunch of dotted lines between the molecules, okay, that are weak forces, but they do affect the boiling point, okay? So they are intermolecular forces. All right, so let's go through them. We're going to go through them individually, but just to be clear, these are the 3. Your book has these awesome summary tables, and I really like them, and it's role of intermolecular forces. They're important in solids, liquids, and gases. And this table actually goes through all of the stuff, like phase changes we just went through. And then we're going to look at properties of gases and solids and liquids later, okay? So this is a very good overall summary table. All right, the 3 forces, 1, 2, 3, increase in strength as we go from 1, 2 to 3, okay? The first one is dispersion forces, and sometimes they're called London dispersion forces. That's the same thing, okay? The second one is called dipole-dipole, okay, dipole-dipole forces. And the last one is called hydrogen bonding, which you sometimes see abbreviated as H bond, okay? Okay, so let's look at the first one, dispersion forces. Everything has London dispersion forces, okay? So let's just look at helium. This is helium. Okay, so if you find helium on the periodic table, you're going to note that it has 2 protons, 2 electrons, 2 neutrons, okay, on the periodic table. So this in the center are the protons and neutrons, the red and gray spheres, and then the little red dot there and the little red dot there, those are electrons. So this is showing helium at any given point in time. So let's say time equals 0 seconds. Time equals 5 seconds, and time equals 10 seconds. So at any given point in time, the electrons are always moving around, okay? Dispersion forces are just resulting from fluctuations in electrons, okay? So in frame 2, we have an electron way over here and an electron way over here. So it's kind of evenly separated within the helium atom. But in frame 3, both electrons are kind of on the left side, and then the right side is empty of electrons. So we generate a partial positive charge just at that second in time on the right side, and then a partial negative charge on the left side, okay? At that given instant, remember, in a container of substance, you've got 10 to the 10th of helium atoms. Remember, if you have 1 mole, you got 10 to the 23rd of these sitting in the beaker or the container. So this frame 3 could occur in, say, 3,000 of them, and then they now have the ability, this partial positive and partial negative can line up. So let's take 3 frame 3s, and they can line up together where we sort of have the partial negative with our 2 electrons line up over here. So this is helium number 1, helium number 2, and helium number 3. And you notice they're all lined up in a row with this dotted attractive intermolecular force between helium 1 and helium 2 and helium 2 and helium 3, simply because of electron fluctuations, okay? But that attractive force does affect the boiling point, okay? So how does it affect the boiling point? Let's look at an example with the noble gases. So if you still have your periodic table out, look at helium. Helium's at the top. It actually has a very small molecular weight. It's like 4 grams per mole, okay? So you're going to have this intermolecular force attraction, but if you have more and more electrons, you could have more and more of these dispersion forces, the higher the molecular weight, okay? So this table on the left did not come from your book, but it's showing the noble gases going down group 8, helium, neon, argon, krypton, etc. And then the corresponding boiling points in Kelvin. Do you see that the boiling points increase simply with an increase in the molar mass? Okay, so that is how dispersion forces would affect the boiling points. Now let's look at something other than the noble gases. If I had, say, CH4 versus C2H6, so I have carbons and hydrogens, a bunch of covalent bonds. They're all nonpolar covalent bonds, but C2H6 has a higher molar mass. Both of them have London dispersion forces, but without even looking it up, I could say that C2H6 has a higher boiling point than CH4. The only thing you need to also consider with dispersion forces is the shape of the molecule. Okay, so this is pentane. This is 5 carbons, okay, with the appropriate corresponding hydrogens connecting so that carbon has all octets. This on the bottom is also 5 carbons and the appropriate corresponding hydrogens, so everybody has the octet, but they're sort of branched out differently. They're kind of branched into this more spherical overall shape, if you see this space-filling shape. So the top pentane think of it as like a big flat pancake. So if you have a pancake, there's going to be a lot of intermolecular forces excuse me, between two pancakes. So the boiling point is going to be higher than this bottom image, because the bottom image, you think of it kind of like trying to stack two balls on top of each other, like two tennis balls. There's only one small point of contact, and so the boiling point is going to be smaller. So shape is the only other thing that dispersion forces you're going to have to look at. If you see, the boiling point is actually listed, and the boiling point of pentane is much higher than the boiling point of this bottom structure that has the same molar mass. Okay. All right, the next force is the dipole-dipole force. And without complicating it too much, you're going to have a polar bond. So that is where you're thinking of the Lewis dot structure, and you're trying to determine if I've got a polar molecule, maybe I've got a positive region. So this blue sphere is supposed to look like a polar molecule with a positive region, and this red sphere is a polar molecule with a negative region. So that was like the delta negative and delta positive. And there is an attractive intermolecular force between the blue sphere and the red sphere that is called a dipole intermolecular force. Okay? You may see them with sort of these kind of regions or clouds that show the partial negative and partial positive region on a molecule, partial negative, partial positive. So now we have an attractive force that you can represent with dotted lines between two molecules or more than two molecules. Okay, so I can have another one over here that's partial positive, lining it up, and that dotted line represents the intermolecular force. Okay, so looking at real molecules, this here would be like an oxygen, and then this region over here would just be a bunch of carbons and hydrogens. So on the right we have a partial negative charge, and on the left here we have a partial positive charge. Okay, so these molecules are this molecule on the right is attracted with a dipole-dipole attraction to the molecule on the left. If you have a beaker of this substance, you're going to have a bunch of these going on. You can have another one lined up on the right, a lot of intermolecular forces. Okay, so if you have a polar bond and you have London dispersion and dipole-dipole intermolecular forces, then the boiling points are going to be higher, because in order to boil a substance, if this was, say, a liquid, in this condition, if we're boiling it and it's changing into a gas, we are breaking, I'll put a little lightning bolt here, we are breaking the intermolecular force here. Okay? So if you look, these are two images from your textbook that show on the left one, these are all non-polar bonds. So the only force present in butane is the London dispersion force. London dispersion, okay? Dispersion. All right, whereas this does have London dispersion forces, but we have a polar carbon to oxygen bond, this dipole here, this dipole. So this not only has London dispersion, but it also has dipole-dipole attraction with the other acetone molecules. Okay? If you look at the boiling point of butane, the boiling point is negative 0.5 degrees Celsius, whereas the boiling point of acetone is 56.2 degrees Celsius. They have the same molecular weight, but because of the extra intermolecular force, it takes more heat to boil acetone. Okay? This BP stands for boiling point. All right, the last intermolecular force is the most important because it's the one students confuse the most, but you actually see it in biology a lot. So it is hydrogen bonding, and it is basically a strong dipole-dipole attraction, but it is a very specific attraction, okay? So I have three examples shown here. Hopefully you recognize that it contains a hydrogen. But what you're going to have is an O, an N, or an F, the three highest electronegative elements, dotted line, attracted to a hydrogen, but that hydrogen must be bound to an O, an N, or an F. Okay? So here would be an example. Let's just pick on oxygen. So I have carbon, and who cares what else he's bound to an oxygen. And he does have his lone pairs. He is attracted to a hydrogen bound to an oxygen, and who cares what that oxygen is also attached to? It's going to have something else. We could even make it a carbon with a bunch of hydrogens, okay? So that would be a correct hydrogen bond, okay? Incorrect hydrogen bond, let's use the same left side, would be a hydrogen, but he's attached to a carbon because, so forgetting about whatever else is on that carbon, you might be like, oh look, that part's correct, that part's correct, oops, this part's wrong, so that is not a hydrogen bond, okay? Incorrect hydrogen bond. So here's two examples from your book of water attracted to other water or ammonia attracted to other ammonia, okay? So here's the water. We have the positive dipole H connected to an oxygen. Dotted line is the hydrogen bond attracted to the oxygen, okay? These are showing the geometry where our lone pairs kind of look like the bunny ears, okay? So if you were to see it in this shape, it looks kind of like the hydrogen is attracted to the lone pairs, okay? Which is totally fine, but ultimately those lone pairs are associated with the red oxygen, okay? And here's an example with nitrogen, because remember nitrogen, O, N, or F. This would be a correct hydrogen bond. A hydrogen covalently bound to a nitrogen on the right, attracted to a nitrogen on the left, okay? And it doesn't matter what the nitrogen on the left is bound with as long as he's got the negative dipole there, okay? It couldn't be like an N2 molecule because that's a nonpolar substance. Or sorry, N2 is triple bond. It couldn't be an N2 molecule because that would not be polar. That would be nonpolar, okay? You see hydrogen bonding, actually, you learn about it in biology class, and this image here is just a Google image that I found. You learn in biology class the 4 bases, A, T, C, and G, and if you haven't learned them, maybe you learned about them in Jurassic Park or something, okay? So you hopefully learn in biology class in high school that T pairs with A and C always pairs with G. But I don't know if you know, these are the structures of T and A. The two sides of DNA, you usually see DNA kind of like a ladder. And you have like maybe A, T, and G with C, and A, T, and G, C, C, okay? And this connection between the two sides of the double helix in DNA is only connected with hydrogen bonds, these dotted lines here. If you see, G and C actually have 3 hydrogen bonds between them. So that's kind of unique. Another force in biological molecules. I know this is a little hard to understand or recognize, but within a protein, the alpha helix shape, this isn't showing all of it, but do you see the red dotted lines along the alpha helix? Those are all hydrogen bonds that keep the helix in that sort of curved spiral ribbon shape, okay? So ultimately, to recap the forces, intermolecular forces, we've got London dispersion, dipole, and hydrogen bonds. The relative strengths, which increase as you go down this list, okay? And then some characteristics. This table here did not come from your book, but if you like this table, it lists the dispersion at the bottom and then dipole, and hydrogen bond. But this table also compares it to the strength of the ionic bond and the covalent bond, and then gives some examples. So if you like this, the strength increases as you go from the bottom to the top of that table. So that table might help you, okay? So let's do an actual example real fast of comparing. So I have 3 substances here, and we need to identify the intermolecular forces that influence the properties. So all we're going to do is you could draw out the Lewis dot structure of the substances, and you could just be clear, all right, nonpolar bonds, therefore the only force is London dispersion. You may be familiar enough without having to draw it out, but right now we're just going to list London dispersion. London dispersion. HCl, well, Cl is one of the very electronegative elements, so if you have HCl, I'll just draw here. He has a negative dipole on the right and a positive dipole on the left. So HCl has London dispersion and dipole-dipole substances, okay? This is actually acetic acid, which is the main ingredient that causes the smell in vinegar, okay? And I know it's a little hard to picture it, so we're going to draw. I'm going to connect. All right. So we actually have positive dipole here, negative. Actually, I'll draw my covalent bond. And then, all right. Excuse me. I'm trying to make a delta. Negative. That's negative. Okay. So this component here can have dipole-dipole interactions, and this component here can form a hydrogen bond with, actually I'll draw another acetone molecule, not acetone, excuse me, acetic acid. All right, so there's the hydrogen bond. So C has all three components, okay? So to recap, what you're going to do if you're given a list and you're trying to figure out, all right, what is who's got the highest boiling point, or put them in order of increasing boiling points. So you need to know the structure. You need to look at the polarity based on the geometry of the substance, and then the boiling point is going to be higher if you've got more intermolecular forces, okay? So A, B, and C, this just goes through exactly what I went through when I drew it, and I listed the forces. So you see how the last one has all three forces. So an increasing boiling point, CH4 is the lowest, HCl is in the middle, and the acetic acid is going to be the highest, okay? So that is the end of the intermolecular forces. The next video will start with section 8.3, which is going to look at gases. So the next video is all about gases. So thank you for listening.